Yeah, please. Right. Thank you, Rambabu. Yeah, fine. So I'll just give you a small recap what we have covered in our previous session. So related to the physical design, we have started with specifications. After specifications, we have done a Verilog coding. Okay, that is register transfer level logic. For that register transfer level logic, we have written a Verilog code. After Verilog code, we have done a RTL verification. RTL verification, in terms of simple terminology, we have written a test bench and we have passed the RTL netlist. RTL Verilog code. And once the RTL Verilog code is passed with its functionality, we have moved it to RTL synthesis. Nothing but converting or translating your hardware description language to gate level netlist. So this netlist consists of technology information, mapping to your technology, and at last step, we are going to optimize our netlist as per the given logic or designed logic we have done in Verilog code. So this is about front-end synthesis part. And coming to the back-end part, we have covered about floor plan. So the main aim of the floor plan is to decide the chip size. That is nothing but die size, core size. Okay. In floor plan stage, we are going to decide die size, core size, and placement of IO ring. Yeah, Bhavani, this is just a recap of the previous classes. Okay. Now today we will explain about the next step of floor plan, that is placement. Okay. So in the floor plan step, we have decided. So how we need to justify or place macros, standard cells, and how we need to arrange macro to macro offset, and what is the main communication between macro to macro, and what are the types of macros we have: soft macro, hard macro. Yeah, Madhu, screen is not visible. Okay, this is old PPT. This is a recap. You should have it in your mind. Already the PPT is shared. Okay, to you. In the floor plan step, we have decided after placing of macros, after placing of standard cells, we have to decide the aspect ratio. That is nothing but height and width of the standard cell. And next is core utilization. How we have calculated the core utilization? This is a mathematical formula using standard cell area, macro area, and divided by total chip area. This will give you the core utilization. The core utilization we are going to give to the chip is 60% at the time of floor plan. Basically, 50% even. Okay, the remaining 50% or the 40% which we are leaving is for signal nets routing, clock nets routing, and ECBOS, engineering change order. This much we have covered in our previous session. Got it, everyone? So for today's session, I'll be sharing you the screen. Hope everyone has understood the recap. So we are going to conclude the physical design sessions in couple of classes, and we'll go to the analog design flow. Now the screen is visible. Thank you, Chakrapani garu. Bhuvneshwari, thank you. So the recap is fine, right? What all concepts we have covered in our previous session? Right. So today we will be covering about placement and CTS. So whatever the estimation or the placement or the standard cells or the macros or the die size or the core size, everything we have done it at a estimate stage. It is not detailed or it is not completely raised. Okay, this is estimation completely. Now, in the placement stage, we are going to do the placement, physical placement of standard cells and macros in the core area. So coming to placement, what is placement? What is CTS and how are the steps going to be and what are the inputs we are going to provide to the EDA tools and how the tool process and what is the tool behavior and that all we're going to learn in detail. Is this fine? Okay. Dear participants, please reply the answer. Are you in a pace or if it is missing your mind blank to understand the concept? If you are missing the connectivity from the old session to the new session, you will be catching a little delay, the subject. Okay. So coming to the contents. So what we are going to learn from this topic. What is placement and inputs to placement? Inputs to placement means, so for the EDA tool, okay, what are the inputs we are going to give at the stage of placement? And in the placement, what are the steps we are going to do? The steps like timing driven and congestion driven placement. And global routing congestion we are going to estimate. Checks after placement. So once the placement is completed, what all checks we have to do? So once you got a bike in your hand, okay, what you will be doing? You will do some checks. What you'll do? You'll turn on the key. You'll press the clutch. You'll turn on the gears, whether it is working or not. You'll start the engine, okay, and you'll accelerate it by using accelerator, and you'll check the front brake. You'll check the back brake, and you'll rev the bike, okay, and the combustion is perfect. Then you'll start the ride. So this much we have to check after the placement. Similarly, how we are going to place the standard cells, how the macros are placed, and how the macros are talking to the standard cells, and all the macros are sitting together. If they are congestion, then how we will be doing routing. All these checks we are to check. Ganesh, please check with the Blackbucks team. So if your friend is unable to connect, okay. Next is clock tree introduction. So what type of clock tree we have to build in our chip? Next is, as we have learned the timing analysis concept, now we have got the CTS clock tree routing. So in this timing concept, I will be teaching you about clock latency, skew, clock uncertainty, clock tree exceptions like sync point, float point, exclude point. Next is CTS buffers list. So to make the delay, to shorten the delay, what type of buffers we have to install? Next is setup in CTS. So what are the tool setups or tool input files we have to check at the time of CTS? Next, checks after CTS. Once the clock tree synthesis is done, what checks we have to do? What analysis we have to do? Physical design is completely estimation, analysis, and making the chip realistic. Is everyone able to understand what are the contents we are going to discuss in this class? If yes, yes, Ganesh has replied. Kirti, Bhuvaneshwari, thank you. So what is placement? Placement is the process of placing the standard cells inside the core boundary in an optimal location. Okay. So this is one of the practical chip. We have done it in 2012 somewhere. Okay. Or 2011. Most possibly older one. Okay. So this, the plus symbol you are seeing in between. Okay. This is completely the standard cells. So I'll make a draw. White. Okay. So the area, whatever you are seeing, this complete area is filled with standard cells. Okay. The white portion. Okay. The complete white portion is filled with standard cells. And on the corners of the core area, we have placed, okay, macros. And on the boundary side, we have placed IO pins on the left side and right side. If you have a, okay, and on the top also, there are few pins. And in the corner also. Okay. So placement is a process of placing the standard cells inside the core area. So we have to place all the standard cells in the core area. For this, what we have to do? We have to load the input file of our Verilog. Okay. After placement, after floor plan. Okay. Just place underscore design. This is the command we have to use. Then the design gets placed. So it will place some randomly. Okay. So we have to arrange it in a proper way. Later on, the placement. The tool mostly places 100% or 99% accurate. If we get any congestion, if we get any violation, then only we have to modify the design. Yeah, Bhuvaneshwari, power rails, that also is there. But power rails can be done later also. Okay. So the top level team has taken care about power rails in this design. So we didn't take care about the power rails. Okay. We have only addressed it to make a part of floor plan, placement, CTS, and routing. That's it. Okay. So this is only placement, floor plan and placement chip. Okay. In this, we have placed macros, we have placed standard cells, and the red region that is very congested. That is hotspot. Like there is more amount of power leakage. And the pink region is also hotspot. And the blue region is also less priority hotspot. And the green region is safe. And the yellow region like cheetah skin is also safe. And the light ash color blues region is also safe. So the only most critical region or the hotspot IR drop region is red and pink. So we can, the tool gives in a color wise symbolic representation for the human beings. So at the time of placement, so we will enter a command called place underscore design. At this time, the tool tries to place the standard cells in such a way that design should have minimal congestion and best timing meeting. 99% tool will take care. What human has to do, what engineer has to do, he has to analyze that the tool is not creating any congestion or timing violation. If these are taken care, then the placement is pass. Every PNR tool is nothing but placement and routing tool. Like Synopsys, IC compiler or ICC2 compiler. In Innovus, that is from the Cadence. Every PNR tool provides various commands, switches, so that the user can optimize the design in a better way in terms of timing, congestion, area, power as per their requirements. Switches means options. So when we are doing the placement, okay, we will get a place underscore design wizard. In that wizard, what it will do? It will give us the options. Timing critical, area critical, routing critical, power critical. If we choose these options, based on that options or switches, okay, tool places the standard cells in an optimal way. Is this clear? The most familiar PNR engineers, they will be doing through command line. And the PNR engineers who are good at GUI options, they will use tool GUI. Okay. So in earlier, when I was working on this PNR, place underscore design. Okay. Initially. So once the placement is done, I used to just check report underscore timing, report underscore area, report underscore power. Okay. If I see any congestion, if I see any timing violations, if I see any power violations, if I see any area violations, then based on that, I used to give place underscore opt hyphen, okay, congestion critical. This is the command I used to give in the tool. Then what it used to do? If the congestion is critical, Okay. So the standard cells has to be moved here and there. So the tool will take care about moving of the standard cells. Yeah, Kavya, my video is off, but the presentation is visible, right? Is my presentation visible, everyone? Yes, sir. Thank you, Bhuvaneshwar. Yeah. My voice is clear, everyone? Clear. Thank you. So my voice and presentation is clear. Then if I turn on video, okay, so the bandwidth will consume more and the voice gets drops. Okay. So we will continue in this way, presentation and voice. Okay. Will it be fine, Kavya? Miss Kavya, are you okay with this presentation and voice? Okay. Any question on this slide? What is placement? So in the last, I will be asking in detail what we are going to do in the placement. Okay. Someone I'll pick and I'll ask you. If you are not, let's see, one time explain again. Good, intelligent person. So in the placement stage, placement is the process of placing our standard cells into the core area. Okay. The tool tries to place the standard cells in such a way that the design should take optimal or less amount of congestion and meets the best timing report. So we have many PNR tools in the market. Example, Synopsys ICC2 or IC compiler or Cadence Innovus. So these tools has many options or commands or switches so that the user can do optimization in such a way that if the timing is not meeting, we have to make a command or switch timing analysis, congestion analysis, area analysis, power analysis. These kind of options, if we are providing it to the place underscore design or place underscore opt switches, okay, then the design will give you appropriate placement without all these congestions or without all these violations. Hope this is clear. No reply. How can I proceed? Yes, sir. Thank you very much. Kavya, your screen is not visible. Blackbucks team, can you please help Miss Kavya? Next is, if you are considering an EDA application, Innovus or Synopsys, okay. So what are the inputs files? We have to give it to the placement tool. That is nothing but .tf file. .tf file has technology information, which has metal layers. Next is TLU plus files, which has max time, min time libraries. Next is left file. Left file also has library exchange format. This also has technology information related to metal width, metal thickness, and all those. Next is netlist. Netlist is nothing but our Verilog file, netlist. Next is standard design constraints. So if you want, so at the time of synthesis, we have given some constraints like clock path, okay, clock source pin. Next is max transition, min transition, input delay, output delay. If we are giving these all these constraints, we have to load that constraint file also. Next is scan depth. So at the time of placement, we are going to define the DFT. DFT comes into picture at the time of placement. So if we want to insert the scanned cells in the design, okay, we will be doing scan depth at the time of placement. And the database of floor plan and the database of power plan. All this we have to give as the input to the tool. What are the inputs to the placement tool? Technology file, TLU plus files, lib files, lib files. Lib files has timing info. Netlist, SDC, design constraints, scan depth for the DFT, floor plan, and placement database. Is this clear? The inputs to the placement tool. Sri Lanka, thank you. So when I was explaining about floor plan, okay, the inputs to the TLU plus files. This contains max and min time libraries, max capacitance, min capacitance, and all those things. TLU plus file. Is this clear, Bhuvneshwar? Table lookups. Okay, TLU plus files, table lookups. So if I have a, so this is my table. R, L, and another one. Resistance, inductance, and capacitance. So my wire length is 1 nanometer. So what should be the R value? What should be the L value? What should be the capacitance value? So all this information is found in the TLU plus files. Rajesh, this is clear? Yes, sir. Thank you very much. Next is steps in the placement. So what we'll be doing in the placement? Okay, pre-placement stage. So before doing the placement, okay, we will be doing a dummy placement. Dummy placement is nothing but whether this placement will work or not. So while we are playing a carrom boards at our childhood, what we will do? First, initially, okay, everyone wants to take a chance and give the strike. So that is nothing but free strike. The same way, in pre-placement stage, we will be doing place underscore design. With this, we will get to understand, okay, what is the estimation of placement. Once this estimation we got it, we will go for initial placement. Initial placement means how we should place standard cells. If you are placing standard cells in the middle of the chip, or in the left corner of the chip, or in the right corner of the chip, okay, that's how initial placement statement. The positions. What will be the good position? So I got a fridge here, okay, whether I should put in kitchen, or whether I should put in the dining area, or whether I should put in the hall, which is a good place for the fridge. Okay, that is how we decide at the step of initial placement. Next is global placement. Global placement means, so we will analyze by placing it each and every position. If we put in kitchen, we may get congestion. Why? Because the size of the kitchen is very small. If we put in dining area, the persons who want to go to the last seat, they will feel uncomfortable. Okay. If you are putting in the hall, okay, it looks awkward whether the visitors comes and directly look straight forward at the fridge. So this kind of global placement we try to analyze. Next is course placement. So at last we have to do one placement. That is course placement. Next is legalization. Legalization means if you are putting the fridge, okay, whether if we can open the door or not. If you are putting in the kitchen, if one person is standing in front of the kitchen platform, if I am unable to open the door, then it is not possible. So we are going to do the legalization. So what we will do? We will turn the fridge towards door open side. That's how we do the legalization. Legalization is nothing but, so whatever the connectivity is good for the standard cells to the macros, or standard cells to the standard cells, or macros to the standard cells, or any kind of means to the IOs. So in that way, we'll go to the legalization. Next is high cells insertion. So we have discussed about, okay, the cells which doesn't have logics, that are high cells insertion. One of the cell is high cells. Next is pillar cells. And all those cells we are going to do this at the time of placement. Next is scan chain reordering. So as we are doing the DFT at the time of placement, we have inserted, we have given the input file of scan-def. Okay. So the scan-def file information has scan cells. So to that scan cells, how we need to arrange the scan cells? That is called scan chain reordering. Next is high fan out net synthesis, HFNS. So I have a logic. So I have fan out of so what will be the fan out of this logic? So 1, 2, 3, 4, 5, 6. So the number of outputs the logic is driving is called fan out. So if these much 6 nets are there, or 6 connectivities are there, so this is fan out. So placing the standard cells, okay, will cause routing congestion, or area congestion, or timing congestion. So these kind of cells or these kind of nets are analyzed at the time of high fan out net synthesis. This is a concept called high fan out net synthesis. Then we will legalize the placement. At the time of placement, we will do check, take care about the congestion, timing, and area for these kind of logics. That is called high fan out net synthesis. Next is iteration for congestion, timing, design revision, and power optimization. So we will do iterations. Iterations means once I have done place underscore design, still I didn't like the placement. I am getting congestion. I am seeing the power hotspots. The previous slide we have seen red color. Okay, that is having more IR drop. So at that time we will take care about power optimization. If it is timing critical, we will be doing about power place underscore design timing critical. So we will do multiple iterations. After doing multiple iterations, we'll try to fix one place. Is this clear slide, everyone? Inputs, steps in the placement. Did everyone follow the slide? What is placement and what are the inputs to the placement? Steps involved in the placement. Yeah, Bhuvneshwari. So at the time of placement, we are going to insert scan cells. That is nothing but for DFT, design for testability. So for doing the scan cells reordering, we will be doing a concept called scan chain reorder. So I have placed one scan cell here. I have placed one scan cell here. And I have placed a scan cell here. and I have placed one cancel here. So if you want to change the order of these cancels, okay, we will be doing the cancel reorder. If you want to remove these cancels, you can remove. This is at the time of placement. Okay. Any more questions from this slide? Sharmaji, please stop asking attendance link. They will not give you the attendance if you post the message about attendance. This is very strict. Shyam, is this clear, everyone? If there is no reply, okay, I consider that no person has understood this concept. Srilata, did you follow the concept? Sushmita, clear. Vijay Durga, Venkata Lakshmi, Manikanta, Rajesh, Akila, Rambabu, Reddy. So, the steps in placement are pre-placement stage. So, what we'll do? We'll try to place the standard cells. We'll check whether this placement suit for this chip or not. Okay, if that doesn't suit, what we'll do? We'll do the initial placement. Initial placement means place underscore design. Next is global placement. Place underscore design hyphen global. Then it will try to check all the possible iterations about placement of standard cells in comparison with macros, communication with macros, communication with other standard cells. Then next, whether the communication is good, okay, then we are going to do course placement. Course placement will give you the detailed placement. If the detailed placement is also having some kind of issues, okay, very less number will. At that time, we want to legalize the design. That time, we are going to use place underscore design hyphen legalize. Then our design gets legalized. Then tie cell insertion. So we are not confident about the design. Okay, we want to tie some cells to logic 0 or logic 1. At that time of time, we are going to do the cells which doesn't have any logic. We are going to insert them. Those are like pillar cells, tie high cells, scan cells, and all those. Next is scan chain reorder. Scan chain reorder is nothing but in placement stage, we will insert scan cells for DFT, design for testability. Design for testability. So whether the logic is working or not externally, we want to pass some test vectors to our scan cells. To that reason, we are inserting the scan cells. This is for design for testability. Next is high fan out net synthesis. So as the image shows previously, okay, one logic has 6 or 8 number of nets connected to one logic cell. Then the fan out is 8. So these kind of cells or nets are identified at the time of placement, and they are specially taken care about high fan out net synthesis. So if we are placing the high fan out net synthesis nets, okay, at the corners, then the congestion, routing, or timing driven analysis has to be taken care. So all this process we will do multiple iterations to meet area, timing, power, and design revision. Multiple iterations, which is suitable for us, then we will freeze the multiple placements. Once the placement is passed, we will go for the next further steps. Clear? So far, everyone? Someone asked me to repeat. Manikanta ji, got it? Sir, Manikanta, got it? Yes, sir. So whatever I explained, okay, performs checks on ports placement. So we will be having ports on the core to die area. So all those ports placement it will check in the placement stage. Performs checks on the end cap cells and tap cells. End cap cells and tap cells are no logic cells. Just they are pillars, just they are cells to meet design for manufacturability. Next, in pre-placement, it will do power planning checks. Okay, the power planning is like if you place the standard cells as a group, whether this VDD and VSS rails are sufficient to supply power to the standard cells or not. Next, perform power plan checks. Next is perform checks on macro placement and use blockages at required places. This is our core area. This is our die area. Okay, these are ports. So it will go for check for the ports placement. Next is end cap cells. Corner filler cells. These all cells are placed. Next is if we have standard cells here in this area. So I am having only one power net. With these two power nets, okay, will this logic be sufficient for power planning or not? This check is performed at power planning in the pre-placement stage. Okay, next, if you place a macro here and we have arranged a blockage also, okay, in pre-placement stage, some standard cells can sit on this blockage also for the communication between standard cells and macros. So intentionally, we have to remove these standard cells and legalize the placement. This check is performed in replacement. Next is see that all macros are fixed. This macro position is fixed. And all macros have sufficient key port margin. Key port margin means for the surroundings, they should have good amount of margin for routing, pins, connection to the standard cells and all those things. So that is key port margin. Next is verify whether all required input files are sourced. What are the required input files? TF, TLV plus files, SDC, .lib, .lef, scandef, Verilog netlist, and floor plan and power plan databases. So these are the input files, whether they are loaded properly or not. Next is density check. So if you are placing the standard cells, it will go for density also. If the more standard cells are placed, there is more amount of poly and oxide. So most of the standard cells are developed on base layers, poly, oxide, metal 1, metal 2, metal 3, metal 4, maximum. Okay. For a full chip design, we will be using metal 6, metal 9, metal 12 layer designs. So to do this density check, we will insert G cells. Those G cells are given by foundry for DF, design for manufacturability. As we do the scan cells placement for DFT, for DFM, we will be inserting G cells also. That is for density limit. if all the standard cells are placed at one location, okay, the density of the pins of the standard cells and the density of the nets routing, everything becomes huge. So to avoid this, we need to analyze the density. We are going to insert the density cells. So reading the information from these cells, we will get the density of that particular coverage area. Clear so far, everyone? Next, make clock idea and use path grouping if required. So in the placement stage, macros to place standard cells, macros to macros, and all this communication happens. Okay, we'll create a ideal clock. So that ideal clock is nothing but it has time. This is ideal clock. And we will be grouping the paths, the standard cells which are sitting here and talking to this macro in the left top corner. Okay. These standard cells are talking to this macro. So we will arrange all these paths in one group. That is called path grouping. Is this clear so far, everyone? Pre-placement stage. Please, someone reply whether you understood or not. If there is any clarity required, I'll explain. Yes, sir, understood. Yes, sir. Clear. Clear. So while I'm asking questions, you should not put blank face. Anjit, thank you. Lakshmi, Kirti, Rambabu, clear. Take clear. Nagur, pick up. So this is how we do initial placement, global placement, and course placement. During the course placement, the tool determines an appropriate location for each cell according to the timing, condition, and multi-voltage constraints. Okay. So course placement is nothing but we will do the placement correctly at the final step. Next is the placed cell doesn't fall on the placement grid and might overlap each other. Large cells like RAM and IP blocks act as a placement blockages for standard cells. So all these are standard cells, the green color ones. Okay, the placement should not get overlapped. The standard cells should not get overlapped. They should be placed in a proper order. So this grid you are seeing, whatever the grid you are seeing, the black side, small black lines. All the standard cells are of same height. Height is same, but the width varies. Okay, there is a thumb rule from the foundry that standard cells height should be same, and their width can vary. So, as an analog design engineer in VLSI, there is a huge requirement for the foundries for standard cells design. Okay, so if you want to become an analog VLSI engineer, okay, you can go for library characterization, like designing the standard cells, and you can make the characterization of standard cells. So if you pick one standard cell, it has different properties. How many metal layers are used in this standard cell? And what is the behavior of the standard cell? what is its timing, what is its area, what is its power, and all those parameters are prepared in one lib. For each and every standard cells, there is a one library file. So combining together their properties, analytics, and all those things, we prepare technology file, library file, lib file, dev file, and all those. That is what called as library characterization engineer for standard cells design. Okay. At the time of replacement, okay, they are doing initial placement, interval placement, or course placement. During the course placement, the tool determines an appropriate location for each cell according to the timing, condition, and multi-voltage constraints. So if we have, okay, some standard cells, if we want to supply 3.3 volts, some standard cells, we want to apply some 2.2 volts or 1.1 volts. So based on the multi-voltage constraints, also the standard cells can be placed. The place standard cell doesn't fall on placement grid. There is a grid, okay? The placement cell grid, the cells doesn't fall on the placement grid. That we have to check. And if the standard cells gets overlapped, then it is a violation. And if we have macros like RAM or IP blocks, okay, then based on their blockages or based on their macro constraints, the standard cells has to be placement taken care. Course placement is a fast and sufficiently accurate for initial timing and condition analysis. So place underscore design. It will not take 10 to 15 minutes to run the tool. Okay. To sufficiently accurately do the placement of standard cells, taking care about initial timing and condition analysis. Place underscore design hyphen after. That is nothing but after variation. This is about course placement. Clear? This slide, everyone? Thank you. Yeah. So next is legalization. So we have the placement. Okay. Sir, can we create two layers? One for standard cells and the other for macros. That is Bhuvaneshwari, your question is not understandable clearly. Sir, Blackbucks, can you enable mic for Bhuvaneshwari? Blackbucks, you are in the call. Please respond.
Yes, sir.
Yeah. Can you please enable mic for Bhuvaneshwari? She has a
Yeah,
question.
okay. Oh, okay.
Yeah. Sham, the overlapping of grid may cause any more power dissipations. So the grid is like this. We have to place the standard cells in this tile size. So we have this grid. Sham, understand this. Bhuvaneshwari, please wait. I'm explaining, Sham. So this is my grid. So I have to place my standard cell in this grid area only. Whether it should take 2 tiles or 3 tiles. If it is placed like this, okay, then it will cause overlapping. So these are communicating the base layers of metals like polyoxide. So that will create a placement logic message. We'll miss the logic of the standard cell at that time of placement. So initially, if we are missing the logic, then the design doesn't work. Okay, Sham, you got it? Power is next level. So initially only, if we are failed to place the standard cells in the tile area, okay, so then the placement is failed. So if you take the example of your house floor, okay, so if you are arranging a tiles or limestone on your floor, so does it look neat if we miss some tiles design or somewhere? No. So the same case here also, we miss the logic or the logic will not work in that instance. Yeah, Bhuvaneshwari, please tell me your question.
So, can we create one layer for standard cells and another layer for macro cells differently, and we interconnect through our layer?
No, no, no. All the standard cells, all the macros. So macro is nothing but a small chip.
IP.
Yeah, IP. So if I am doing an SOC, okay, my IP is wireless chip. I have Bluetooth and Wi-Fi module in that. So that is having 4 metal layer, 6 metal layer design. Okay, if considering
Okay.
the standard cells, I am designing each standard cells till metal 2. Poly, base layer, oxide, base layer, metal 1, metal 2. This is my standard cell. So all the designs or all the standard cells, all the macros has multiple layers. So they are to be placed on a stack. So if you are building a 10th floor building, okay, it builds on pillars connecting vias. And the slab is floor plan. Each and every slab has uniqueness. And the layout of placement of rooms can vary. The similar way we follow in chip design. Is this clear, Bhuvaneshwari?
Yes, sir.
Yeah,
Fine.
done.
Thank you, sir.
Next is legalization. So how we have to legalize the design? During legalization, the tool moves the cells to legal locations on the placement grid and eliminate any overlap between cells. So legalization will take care. Okay, in the previous slide, we have seen all the standard cells are being overlapped and they are not tile oriented on the grid. So once we press the command or the switch, placement underscore design, legalize. Then the nearest communication standard cells will come sit together and connect to the tiles in a grid. As per the grid, they will legalize. They will not overlap and they will eliminate congestion. These small changes to the cell location cause the length of the wire connections to change, possibly causing new timing violations. So once we do the legalization, we may get timing violations. Why? Because the standard cell communicating here wants to communicate with the standard cells. So how the routing is possible? So the connection net becomes more length. So the delay also increases. So how we need to avoid this violation? So what we'll do? Either we'll insert delay buffers which can drive the data very fast, or we'll move the standard cells near the location. That is another kind of function. So the legalization of placement can do the wire connections to change the possibly the new timing violations. It may give the legalization violations, but we have to do the legalization. Why? Because the placement itself, the standard cells of the placement itself is not appropriate, then the chip is collapsed completely. Such violations can often be fixed by incremental optimization. Place underscore design, okay, optimize to maximum level. So that is nothing but resizing by the driving cells. So I can give the drive strength. I can increase the drive strength of the standard cell. How to increase the drive strength of the standard cell? By inserting buffers. By inserting driver cells. So that we will get it from the library. Okay. So as we see in the racing bikes, we have normal fuel. Okay. When we turn on nitrogen, the bike starts very quick fast. Sir, is it not necessary to place the standard cells in a linear manner? Shravya, what is meant by linear manner? So we have a thumb rule, okay, for the placement of standard cells. No, not actually one after the other. So so this is a real life example. When a new boy gets married to a new girl, okay, what is his connections? Basically, his life partner, his parents, and their parents. And next, after their parents, they will get the connection with other family relations. Okay, his uncle's brother, his mother's sister, like that, we will get the connections. The similar way, okay, the basic standard cells or the logic which is more with the standard cells, they place at one side. Okay, the remaining standard cells surround them together to get the logic communicated very easily. Got it, Shravya? It's not like arranging brick on a brick, brick on a brick. We should not do that, basically. If we are doing like that, it is manual. Then we should not go for the physical design. We should go for manual placement. If we are going the manual placement, you have some n million number of gates. Will you do that? Is it possible for you to complete the design in 1 month or 1 year? No, it is never possible. To place manually the standard cells, okay, in a linear manner. It can be placed in a random manner, but they have to follow the thumb rule. They have to be placed in a grid or tile regions. Okay. Done. I hope this slide is everyone clear. Bhuvaneshwari, Shravya, Shaikh. Today proceed further. Ishwar. Ishwar Sai Royal. Rajesh. Thank you. Rambabu. Thank you. Kenalaka. Next is Thai cell insertion. So here, what is this? Okay, what is this circuit? What is the circuit? The most famous circuit. Yes, it is CMOS, combination of PMOS and NMOS. What is the logic there? Yeah, everyone answers. Yeah, correct, Shiva Ganesh. Shiva Ganesh is the right person. Okay, Madhu, correct. Everyone is answering, giving, yeah, Chaitanya, good, good. You are very intelligent like me. CMOS inverter. Amar, right. So, this is a inverter logic which is built on MOSFETs. So, how the tie cell insertion happens? So, if we connect the input line, okay, here, and agree. So, if we tie this input line directly to the VDD, okay, this cells get damaged. We may give here 3.3 volts. Even though my net has RC values. Okay, the cells get damaged directly if we are giving VDD. So when we want to tie the logic to 1 or logic to 0, we will be using tie cells. The tie cells, every time I want to keep this inverter logic 1. So that the output will give you logic 1. The output will give you logic 0. So I want to tie this cell to 1. so that the output will give you 0. So that this is dependent to other laws. So in that case, we will give you the tie cells. This is how the placement tie cells are used. So this is all something English, the descent. Sometimes in the netlist, some unused inputs are tied to VDD or VSS. Okay. So the synthesis tool doesn't understand unused nets. So this is very important at the time of synthesis. So if you report design, check underscore design, okay, if there are any warnings of unused nets or errors of unused nets, then we have to take care about these nets. So synthesis tool does whether it connects to ground or VDD. If those are connected to VDD and ground, my transistor gets spoiled. It is not recommended to connect the gate directly to the power nets. So we connect the gate to tie high or tie low cells. The placement tool does optimization of tie cells. Scan chaining order reduces wire length of the timing improvement for the scan chains or tie cells. Scan chain reordering minimizes congestion and improves routability. So if the tie high cell is somewhere sitting, okay, and I want to connect this net here, so the routing is not possible here, okay, then what we'll do? We'll do the scan chain reordering to place this tie high cell here on the period cell output pin. That is how the scan chain reordering minimizes the congestion and improves routability. Is this clear, everyone? For the simple transistor logic, CMOS inverter. Amar, Madhu, Bhuvaneshwari, Himalata. Everyone is able to understand tie cell insertion. Sadik, after a long time. Bhuvaneshwari, explain once again. So, at the time of synthesis, there are chances or possibilities of unused nets. So, these unused nets of the logic are tied to VDD or ground. If you are tying the nets to VDD or ground, the cells inside the logic gets damaged if you connect them to power. Okay. So to avoid this, we are connecting these nets, unused nets, to tie high or tie low cells. Tie high cells will give you logic 1. Tie low cells will give you logic 0. The cells are designed like that. The placement tool optimizes the placement of tie cells also. Scan chain reordering also take care the wire length of the tie cells to the logic connectivity to improve timing analysis. Scan chain reordering will take care about minimizing the congestion in the placement of tie cells. Clear? Bhuvaneshwari, Swavya, Rambabu. See, learning theoretically is very easy. Okay. While doing practically, you need to do multiple iterations. So I remember for one design, I have done almost all 17 iterations of PNR, just PNR. All the time I get iron drop analysis, congestion, timing. Every time. And the chip size is very small. And there are almost all 17,000 million gates. Understand? 17,000 million gates, the gate count. And there are 4 macros. To place 3 mm by 3 mm, the chip sizes. Okay. That is including the area, core area. Okay. So almost 1.9 to 1.8 something, 1.7 by 1.7 mm. I used to get the core area. In that core area, I have to place this 17,000 million gates with 4 macros with 70% of core utilization. Okay. And I got 77% core utilization. Okay. So the core utilization is more. So where can I get the routing? Where can I get the clock net? Where can I get the power net? So I was facing all these violations. So 17 times I did this iteration. From PNR to placement to routing, placement to routing, placement to routing. Almost all I spent 7 months. So if we are displaced, the logic doesn't work. So for this, there is a check. Sharan Reddy, good question. So if there is any logic mismatch, okay, the chip is not accepted. Definitely. So what we do, each and every step, like floor plan, basement, CTS, routing, each and every step, we get the output of Verilog netlist. We'll take that Verilog netlist and the initial, at the time of RTL verification, we have Verilog test beds. This netlist will give the input to the tool for logical equivalence checking and the code coverage and the timing coverage and everything. So there is every situation, there is a check. That verification is called formal verification. Clear, Sharan Reddy? Very good question it was. Yes, sir. Sir, how can we check IR drop report like if one gate is making issue? So report underscore power. Okay. So we'll get a huge bunch of report. To read that report, to get a big headache, it will take 1 hour, 1.5 hours. Definitely. If you are having 17,000 million gates, not 70,000, 70 million gates. Okay. 17,000 million gates. Karan, okay, understand how big the design is. Okay, I am only the physical design designer there. So I have a team of 4 members. So all the 4 members, we used to work on the same design. Okay, running iterations PNR, running iterations PNR. If we run one PNR, okay, one day, we used to give runs for 1 week for multiple iterations. For one run, it will take almost all 6 to 8 hours. Okay. So this is how the time critical consumption, why it took 7 months. That is all the different story. Why? Because when we give the placement underscore design, okay, then we have to sit there. We have to check the design. We have to read the report. We have to read the log file. We have to analyze parallelly. So if we get an error, we need to highlight it. We need to put it in our Dropbox where the error came and all those. So everything is scripted. We need to script everything. We need to write TCL commands. So where the error has to go and sit, where the report has to go and sit, where the warning has to come. So like this, we all 4 people will work. Only one person is to run the PNR, one person is to check for timing, one person is to check for power, one person is to check for congestion. So all we used to sit together, we used to run the code, place underscore results. Then we used to analyze the logs, reports, and this. So check underscore design. Okay, this one will give you the report of the complete design. And next is report underscore power. Okay, so if we have any power issues, okay, in detail we have to go there and we have to understand in the report and elaborate the report with the commands. Then we can get the IR clear. Is this clear, Bhuvneshwari? If the IR drop for particular cell is more, okay, we need to report that cell also. And whether we have any alternate cell in placement of this cell in our library. If we have, we'll remove that cell and we'll place it. This is very less chances. The tool take care of it. You can earn more than Jagan in the property. that much amount of salaries you will get. Okay. Next. You are afraid, Asad? No. I am encouraging you people, Shravya. So afraid is a different part and making you keeping the interest of the subject. So even initially I was afraid when I was learning VLSI subject. Okay. I am the only one person of my BTech engineer who got settled in VLSI. And the remaining all people, they got into the jobs of signals, railways, and some are into the business, and some are into the embedded, some are into Linux device drivers. And couple of my friends who are working along with me in VLSI, they are into the testing domain, but not into the pure chip design domain. Once we get the chip, okay, out, they need to connect it in the chip testing design. So I'll show you that chip testing equipment also. So we have this nano characterization and nano fabrication labs. So these labs, we will do this kind of analysis. So we'll call this probe station and cascade. Okay, these kind of machines we use. So I can show you the image of probe station cascade. So similarly, like this big device, big equipment like this. Okay. Similarly, like this big equipment, we will be having a chip here. We need to place the chip here. We need to probe the, we will be having very tiny leads. See, the leads, very tiny leads. By using microscope, we have to move the leads onto the chip to connect the metals. And we need to understand the analysis. We will be having different kind of analysis meters. Okay, spectrometers, network analyzers, and signal generators, function generators, and all these will be having. So everything we have to pass the values to the probe station. The probe station will be connecting, and this is a closed chamber. The chip will be closed. It should not get intact with the air also or dust also. Then the results are not appropriate. All these are different brands of probe stations. So this kind of equipment we used to use for testing. So most of my friends are working in this field. So I am only the person who is working in VLSI chip design. And most of my friends are working in VLSI testing. Is this clear, everyone? So people be passionate about learning. Okay, I'm not making you afraid. Okay, I'm giving you the enough knowledge how the career path is in VLSI. Hope it is clear, everyone. It is very interesting learning the VLSI subjects, but you should pay very much attention. You should, unless until you get water in the ground, you dig a borewell. That uh, attitude you need to have in the VLSI subject. Unless until you get the subject completely, you need to dig it. Okay. So if we start a borewell at one corner in our house, it has reached 300 feet. It has reached 600 feet. But we are not satisfied with the water quantity, what is pumping out. But if we dig for 1,000 feet, definitely it is very well and good. We can survive for not less than 10 years or 20 years. That much we have to dig in the subject of business. Yeah. So the people who are from KGR college, KGR, KGR in Hyderabad, and GB group of students, Bits Pilani, Chanapet. So those people get in touch with me when I gave you this best lecture for seminars. So they asked me, "Bro, how are you, sir? What country you are working?" Like that. They are into the VLSI industries. Yeah, and Vietnam, even Hyderabad is like that. In my building itself, they have big almost 1800. Okay, but still we get the campus. That is our situation. What we have to do? We have to survive. Survive. Next is, so my example was clear previously. High fan outlet synthesis. Okay, so high fan outlet synthesis is nothing but at the time of synthesis, okay, we get analyzed whatever the cell is, okay, the main logic cell. Here the logic cell is A. So A is having 1, 2, 3, 4. So the fan out of A is 4. To reduce the fan out, what we will be doing? We will be doing buffer insertions or cloning. Okay, the cloning means A will be cloned to have A1 and A2, and the logic will be split. So the fan out of A1 is 2 and fan out of A2 is 2. So this kind of analysis we will do, and we will reduce the high fan out rate synthesis, congestion, timing critical, area critical, power critical. And the placement of these standard cells are done very neatly. And if you do buffer insertions, A is having buffer, A is the driving cell, and C1, C2 are the buffers. So these buffers has very less amount of delay and even zero delay also. But the logic reaches B1, B2, B3, B4 in time. But the fan out is split. Okay. So if you are having luggage of 2 trolleys and 1 shoulder bag and 1 handbag in your hand, is it possible to carry them easily? No. What you will do? You will accommodate another person to help you to drop in the bus stand, railway station, or airport. Right? Or you will take a help of trolley. The same way, here we are taking another person help, or we are taking a help of trolley. Clear? Does it make sense, everyone? Purna Durga, once after the explanation, you tell me that your voice is not clear. Okay. So did you understand what is the concept? Durga. So high fan out net synthesis means, especially Durga. Okay. So high fan out net synthesis means the nets having more amount of driving cells like this. B1, B2, B3. One cell is having 4 number of driving cells. So this is not good for the placement. And the driving capacity of the A cell will degrade. So to degrade or to improve the driving capacity of A cell, what we'll do? We'll do the concept of cloning. A1, A2 will be using cloning cells so that the load will be distributed. Else, we will be taking the help of buffering. The buffering of C1, C2 cells will distribute the load. Clear? Everyone? So far, I fan out net synthesis. Rakesh ji, Durga, you are able to understand? Yes. Is there, if there is high fan out, it leads to power dissipation, sir. How can we overcome that? So using the cloning, using the buffering only, we can reduce the power dissipation. Okay. So even suppose if the drive strength of A is 5, okay, each and every cell requires a 5 drive strength in equal amount of time. Is it possible by A? No. So what we'll do? We'll give this 5 to A1. We'll give this 5 to A2. So this 5 value can be given in time to all the 4 logics. If you are using buffers, these are faster driven buffers or high capacity buffers or reliable buffers. which can improve the performance of A. Then this 5 value can be carried very easily to the end steps. So we are using the concept of cloning and buffering. The time taken less will consume less amount of power. Okay. Power is nothing but VI. So current is anyhow constant, the voltage varies. We can assign delay in Verilog code without you using buffers. No, sir. No. Actually, at the time of Verilog code, we don't understand about fan out. Okay. After synthesis only, we'll get the concept of fan out. Got it, Sharon? At the time of Verilog, we write only English code. Okay. We don't understand about fan out or synthesis or what cell has to drive what net has to drive what. We don't understand anything about the physical implementation. We'll have only the logical implementation. That is very long term. Once after starting the placement or synthesis only, we'll get to know what is a fan and how many nets are having synthesizable nets and how much logic is driven. That only we'll get after synthesis. The first step. Sharon, is it clear? Yes, sir. Thank you, Sharon ji. Better election. Thank you. Next is placement optimization. In this stage, tool tries to optimize placement to reduce congestion, improve timing, and to fix design. The placement optimization. First it will start. What it will check? Large timing, large power, large congestion availability. If it doesn't have those, we'll go for check for mild congestions. If we have mild congestion, we'll refine the placement. If it doesn't have that mild congestion, we'll check for small timing power violations. If we have the small timing power violations, we'll go for the incremental placement. Okay, incremental placement, what it does? It does placement optimization. On top of it, another placement of. What we'll do? We have a teddy bear which is filled with foam. Okay, we have put it in a polythene bag. I want to compress it to a box size. What we'll do? By taking out the vacuum, we'll compress it to a box size. The same way, placement optimization and incremental placement optimization does. And still we have issues related to timing and DRC. Okay, we'll do rerouting optimization. That we'll check in the later stages. Placement optimization is clear. What all the steps will take care in the placement optimization tool does? Cell resizing, buffering, pin swapping, logical reconstruction, or voltage swapping, cloning of cells. All these options tool will take into picture. I have more amount of delay. So I want to reduce the delay. What it will do? Cell delay is more. How to reduce the cell delay? I want to use less size cell delay. Then I will go for cell size. Okay. The output pin of my cell is having more voltage. Then what I'll do? I'll change the port by voltage swapping. Fan out. Okay. And if I want to increase the delay, if I want to reduce the delay, I'll go for buffering. For fan out, I'll go for cloning. And the pin swapping. Pin swapping means I have connected to 4 logical inputs. The pin is having very less density. Then I have to go for pin swapping. So my logic itself is not working properly. Okay. Then I'll go for logical reconstruction. Logical reconstruction means that is checking after placement. I'll take the very long netlist of placement and give it to the tool with RTL verification. Then I'll go for the logical reconstruction to meet the design requirements. Clear everyone so far? Placement optimization stage. Yeah, thank you. Next is timing driven placement. So in the example, in the slide, okay, if you see, this is the one corner and this is another corner. All these white dots are connecting to the cells, which is virtual route. To make this virtual route, okay, this long net is not preferable for the routing. To make this timing driven placement, we need to rearrange the placement. So the cells which are talking near to the cells, we need to rearrange. So what? We will be getting the timing driven placement. If we click on one cell, it will give you the fly lines. That is to which cell it is talking to. So that we can rearrange the cells. Clear? Timing driven placement. Next is congestion driven placement. So I have a lot of congestion. Okay. So I'm unable to route the nets. So here you can see the placement in the example. Okay. In any region, the placement is more than 7 or less than more than or equal to 7, then there is a congestion. If it is less greater than or equal to 6, then it is higher. Orange is okay, allowable. Yellow is allowable. Green is allowable. And greater than 2 is also allowable. So the congestion driven placement. To reduce the congestion, like placement of cells, placing beside by beside, okay, and pins, routing the nets, and logic, routing the nets, all this has to be minimized. To reduce that, we are giving place underscore design hyphen hyphen congestion driven. Then it will go for congestion driven placement. So it can be done in this way. So this is unroutable layout. So make the routable layout. Here we have congestion. Okay, the red net. To avoid that red net congestion, we have placed the logics in a different way. Even though we have longer wire length, okay, but no congestion. If we have longer wire length, the net delay may increase, but the drive strength can be increased by inserting buffers. This is how we do congestion aware placement. This is an example. Next is global route congestion. Global routing congestion makes the comparison of estimated routing net and detailed routing net. So I want to reach Tirupati. from Hyderabad to Tirupati. I can reach in two directions on the roadways. I can go to Vijayawada, and from Vijayawada, I can go to Tirupati, or else from Kurnool, Kadapa, I can go to Tirupati. These are the two possibilities. So from Vijayawada, it will take more number of time, but from Kurnool and Kadapa, it will take less number of time. But the road feasibility from Vijayawada and Ongole, that road is very clear. It is 6-lane or 4-lane road. But from Kadapa Kurnool, it is 2-lane road. So this is how we need to check the trade-offs. So this is the comparison the global route does. The routing comparison between virtual routing and detailed routing, global routing does. So it is a difference between available routing tracks and required routing tracks to fix the congestion. So I have both available routing tracks to reach Tirupati, but which routing track I need to choose for my journey? That is given to global routing. Partitions chip into global routing cells. So there are some G cells. So partitioning is a what congestion means? Congestion. So if you eat more food in your stomach, what will happen? Are you able to sit? Are you able to feel comfortable? No. The same way, the design also has congestion. Area congestion, timing congestion, power congestion. So if I eat more spices, I'll have more amount of burning congestion. If I eat more cold, I have throat infection congestion. If I eat full amount of stomach, then I have problem of moving. Then it is area congestion. Is it clear, everyone? Okay. Flavia, congestion is nothing but keeping all together at one location makes it congestion. Partitions shift into global cells. So if there are more number of routing nets, so whatever the partition it has made, the chip or the tool, so it has made into a grid. So this grid is called splitting your design to global cells, which are having global routings. So these global routings are more, then we have more amount of congestion. If we have less amount of routings, we have less amount of congestion. So global routing will partition the chips for global routing cells and assigns nets to specific paths to meet the metal layers. Determines each global routing cells has enough amount of routing space to avoid congestion. Rajeshwari, what is that? Clear, sir? Sir, open first slide. Why to open first slide? You have any doubt? You want to take a snapshot? And what are the concepts covered? You want to put it in your attendance link, right? Rajeshwari, is this correct answer from my side? Yeah. Global routing is clear for everyone? Thanks for your honest. Yes, sir. Strategies we follow for fixing the congestion. Once we run the course placement, okay, this is detailed placement. So we have acceptable congestion, we need not modify the placement or we need not modify the floor plan. We will legalize the placement and we will legalize the constraints. If we don't have the congestion, we'll proceed further. If we have congestion, then what we need to take care? We need to modify the physical constraints. What are those physical constraints? Rerunning the course placement with congestion driven option. Adjust the cell density in congestion areas. Adding and modifying the blockages. Moving macros. Changing core shape or size. Moving pins or pads. This is how strategies we follow to fix the congestion. So what we eat more food, what we do, we'll take lime soda. We may take diazine tablet. We will do walking. So all these steps we follow to avoid human digestion congestion. Clear so far, everyone? Clear. So I hope this much topic is enough for today. We'll proceed for the next session and complete the placement CTS and routing. And we will do a practical chip design using the Cadence Innova tool till routing. And we'll end the physical design and we'll move to the analog circuit design part. Is everyone clear with this? Yeah, thank you very much. So I need your feedback. Was the class informative? Whether you are able to learn, understand the concept, as this is very new to subject to you. So if you are BTech candidates, this is very new subject to you. No, I don't need any 5-star rating or anything. So whether you are able to catch the subject or not, whether you are able to understand or not, is my intention. Yeah. Thank you. Good night all. Okay.